Okay, yeah, I'll operate.
Okay, welcome everyone. Maybe we can get started. We're very happy to have Rajath Radhakrishnan with us today, who's going to tell us about gauging non-invertible symmetries in 2+1d.
Yeah, thank you for the opportunity to speak. So today I will discuss about something that we all do in energy physics, which is gauging symmetries to create quantum field theories. But today I would like to introduce these non-invertible symmetries, which are a bit more weirder cousins of symmetries, and try to see what they have to say about quantum field theories and what it means to gauge those symmetries. So that's the topic. So this is based on upcoming work with Mahesh, Matthew, and Clement. So we know that when we usually start with some quantum field theory, you have some Lie group type symmetry, and we gauge it to construct new quantum field theories. But more generally, when we have this, if you have in mind some space of QFTs, gauging is a method that allows you to go between different QFTs. And sometimes you can also have some duality, which is uncovered by gauging something. So you start with a QFT, which has some symmetry, you gauge it, but after you gauge it, you go back to the same theory. So sometimes gauging can be a self-duality. And when that happens, gauging can tell you about some degeneracy of states in your QFT, because gauging basically rearranges some things in your QFT, but you are getting back what you started with. So there should be some degeneracy of states, for example. So there are various ways in which gauging symmetry shows up in quantum field theories. But now we are looking at much more general notions of symmetry, which goes by this slogan that whenever you find these special operators called topological operators in your QFT, you call it some symmetry that you have. And then if this, in this very generalized framework of symmetries, then you can ask, can I gauge these symmetries, these generalized symmetries, and what does it tell us? So in particular, there are some special topological operators, which are called this non-invertible symmetry, which arises from relaxing like a sacred axiom that you have when we call something a symmetry, which is invertibility of a symmetry. When you have a symmetry action, there should be an inverse. But if you look at the topological operators in your favorite QFT, it might happen that that QFT will have some topological operators whose action is not invertible. So somehow you have to live with this, and if you say that every topological operator implements a symmetry, you have to take this into account. So that's why people now call it a new name, which is non-invertible symmetry, simply because their action is not invertible. So this will become clear what I mean by these words in some concrete examples. So why are we okay with relaxing this crucial property of a symmetry that it has to be invertible? Why are we okay with calling it a symmetry, even though it's not invertible? So that is one question. So the thing is, these operators exist in many QFTs. Now the thing is, if we think of it as a symmetry, then we can ask very meaningful questions about that operator. We can ask questions like, can I gauge that? And sometimes they are gaugeable. And when you gauge these symmetries, you get some maps between QFTs that you did not have before. So there may be QFT1, QFT2, which are not related by any usual gauging. But QFT1 has some non-invertible symmetry, and you gauge it, you get QFT2. This can happen. So we will see an example of that. Sometimes you cannot gauge non-invertible symmetries. So this is like for ordinary symmetries. You cannot gauge it. There's some anomaly. So, and the anomaly is some quantity that is very important because it's an RG invariant. So, yeah. Yeah. It's in particular, because I'm constructing those defects in particular by gauging, that interface is a topological interface, so I can move it. So that's one picture you can have. Yeah. So sometimes you cannot gauge the symmetries, and that gives you more anomalies. And sometimes the ordinary symmetries that you have in your QFT are not anomalous, so you don't a priori get any constraints on your RG flow. But sometimes these non-invertible symmetries come with an anomaly. Then you can use that anomaly to study what happens in the IR. That is one thing that you might want to do. Now, on the mathematics side, a lot of development in this higher fusion category and higher representation theory is closely tied to non-invertible symmetries. And the reason is that when physicists started using groups in physics, a lot of finite group theory and representation theory were known or worked out, and we could borrow a lot of results from that to apply it to physics. But these non-invertible symmetries, the mathematical structure that one should define, what is the right thing to even write down, is still being discussed. So it's an interaction, constant interaction between mathematicians and physicists, where you try to write down what is the right set of axioms that you need to describe these topological defects. And therefore, in a way, this is an interaction between these higher category theory, because category theory turns out to be the right mathematical structure for describing these defects. So it's closely tied to the category theory, and there's also a representation theory for the symmetries, and that is what I'm calling higher representation theory. And you can also have a generalized Landau paradigm. So if you're a condensed matter physicist and if you want to study phases of some lattice models, or you could do it even for a QFT, you want to describe phase transitions and you want to describe different phases using symmetry breaking. But now you have more symmetries. So there are more ways in which that symmetry can break. So more phases. So there's a generalized framework of, there's a generalized Landau paradigm which is based on these generalized symmetries. So that is going beyond ordinary symmetries. Finally, you may be a quantum information theorist who is interested in developing error correcting codes, and you may be also interested in quantum simulation. There are, at least in the last few years, and even before that, there are some concrete relationships showing up between these non-invertible symmetries and measurements. So, and measurements are one of the most important non-unitary things you can do. And measurement is not invertible, and so is a non-invertible symmetry. So let's just say there is some relation, but there is actually a concrete relation. So let me start with a concrete QFT to explain my motivation to look at gauging symmetries. So I start with the BF theory. So this is a three-dimensional theory. I have two U1 gauge fields, and I have naturally a class of operators which are line operators. So I have some one forms, I integrate it over some loop, and I define two types of line operators. I call this one E, that one M. I can have their composite, I call it psi. I mean, these discrete gauge theories or BF theories are not the first QFTs that we learned, because these are rather trivial QFTs in a way, because everything is topological. There's not much dynamics going on. But on the lattice, this is a very, very important lattice model, which is called the toric code. So I will describe a lattice version of this because that will be important. So the lattice, you can take it to be a square lattice on a torus, and each edge has a qubit living on it. So each red dot that you see is a qubit. And this is the Hamiltonian. So you take a placket and you have the Pauli Z operator. And for every vertex, you have a Pauli X operator. And this is how you're defining the Hamiltonian for your system. And this is the lattice version of the BF gauge theory that we saw before. And this was introduced by Kitaev in 1997. So there are these line operators. We saw these EM psi line operators. They are excitations on the lattice. So these are, on the lattice, these are implemented by certain ribbon operators or line operators. And they also have a notion of spin. So one is like no excitation. So it's the trivial line operator. E and M are bosons, and psi is a fermion. That is how the spin of these excitations. And they also have a notion of braiding, which comes from braiding of two line operators, and this is given by this matrix. So you choose E and M, they braid non-trivially, E and psi, they braid non-trivially, etc. So these are things that you can compute about the anyons of this lattice model, and they correspond to these configurations for the line operators in the continuum. So this is the data of this model. So this is a particular example, and you can, this lattice model a flat version of this, not on the torus, but a flat version of this with boundary condition is one of the most important quantum error correcting codes that you can construct. In fact, 2024 was an interesting year because Google actually realized this in their lab, and they tried to show the error correcting properties of this model in the lab. So because you can actually create based on whatever your qubit is. Your qubit could be something superconducting, your qubit could be an ion. Based on whatever physical realization you have for a qubit, you can realize this model. Now, there is a generalization of this model for any finite group. So the example that we discussed in the previous page is Z2 group. For a general group, you can still write down a lattice model, square lattice, where each dot is now not a qubit, it is a size of G dimensional Hilbert space. So if you have size of G dimensional Hilbert space at each lattice point, you can still write down these operators and define a Hamiltonian and still study the properties. This is a generalization of the Z2 case that we saw above. And the continuum of this is the 3D Dirac-Witten theory. So this is the lattice model for the Dirac-Witten theory. And again, this theory is also topological. It has a bunch of line operators in it. And the anionic excitations of this lattice model. So whenever you have violations of these operators, you can call it an excitation of the lattice model. These excitations correspond to line operators of your continuum theory, and they can be labeled as we usually call it, like electrically charged lines, magnetically charged lines, and dionic line operators of the discrete gauge theory or Dirac-Witten theory. So one way in which you can label the line operators is in this way. You have a label coming from when you have a magnetically charged operator, you have a dependence on the conjugacy class. You also have a dependence on the representation. So you choose a conjugacy class for your gauge group, and you choose a representation of the centralizer of the gauge group of this G. So this is the data that shows up. If this conjugacy class was trivial, the pi is just a representation of the gauge group. This is like the Wilson lines you have. If this representation was trivial and conjugacy class was non-trivial, it's like the tough lines you have in the theory. Of particular interest to me will be this model when the gauge group is S3. And I will explain why that is interesting. Yeah.
Continuum limit. Is this a lattice model? Is this already in the continuum limit, or you're doing some parameter?
Yeah, so in this case, usually when you describe the Dirac-Witten theory itself, you can choose a triangulation of the manifold and you put gauge fields on it. And there is not really any dependence on the triangulation. It's already in a way a continuum limit because it's a topological theory. So,
oh, I see.
Yeah.
So there you had Wilson line.
Yeah, so on the lattice, it's about if you have an excitation or not. So you ask what is the ground state Hilbert space, and do you have an excitation or not? And the different excitations are labeled by which of these operators does it not commute with. And that is the same data that is secretly there in this way of labeling. To recover this labeling from here, you have to study what algebra these operators form and study its representations, and you will find the same set of data. So the line operators that you have in the continuum are given by excitations on the lattice. So what you can think of is you have a loop of line operator in the continuum. You slice it, you take a space-like slice, you cut the line at 2 points. So on the lattice, you have 2 points where you have the anions connected by a ribbon operator. So anions always occur in pairs on the lattice, and that is because in the continuum picture, you have a loop of the line, you're cutting it, and you cut it at 2 points. That's the picture. Yeah.
So if you, in your toric model,
yeah,
if you put that thing on torus, the ground state is 4-4 degenerate because of this.
Yeah.
So I'm asking the same thing. What happens if you put it on torus? The ground state is still 4-4 degenerate, or because that 4-4 degeneracy comes because of this two Wilson operator.
Right.
So that's what I'm asking.
No, yeah, here. So here it's not 4-4 degenerate. It is square of the dimension of the size of the group. So in that case, it was a Z2 based model. That way it was 4. So it will increase with the size of the group.
The dimension of the matrix.
Yeah, so the dimension. So what are the GDITs that you use? The size of the group G, the size of the ground state, ground state Hilbert space, the space of ground states will grow with the size of G. Yeah. Okay, so let me just explicitly write down all the line operators in the S3 theory, because it will be important to just know what are the number of these line operators you have in the S3 case. So in S3, you have these conjugacy classes. The centralizers of these conjugacy classes are these. The full S3 is Z2 and is Z3, and you write down all the irreducible representations for each of the centralizers, and you just write down all the lines. What are all the lines? You get 8 line operators. So these 3 are the Wilson lines based on just the representations, and you have S1 and R1, which are like the tough lines, and you also have some dionic lines coming from composites of these lines. So you have 8 line operators. So this number 8, counting 8 will be important in what I'm going to say. But these are the set of line operators in this model. Now, there is, yeah.
Was the discrete group or the manic group?
S3 is the permutation group of 3 elements, yeah. So it is known that there is a way to get S3 Daggraviton theory from Z3 Daggraviton theory by doing a gauging. So you start with Z3, you write down the model. That model happens to have a Z2 symmetry. If you gauge it, you get S3 Daggraviton theory. The details are not important. You just have to keep it in your mind that S3 is a semi-direct product of Z2 and Z3. So it makes sense that you have some kind of gauging to construct S3 from Z3. What does it mean? It means that on the lattice, suppose you can realize the Z3 Daggraviton theory. Suppose you can realize the gauging map. You can construct the S3 Daggraviton theory from the Z3 on the lattice. So that is something that is explored in this paper. And in fact, they go ahead and realize the Z3 theory in this quantum processor of Continuum. So Continuum is a company which have a quantum processor where the qubits are given by ions. And you can try to realize the Z3 Daggraviton theory on it with some interactions and try to see what it takes to realize the S3, what it takes to realize Z3, what it takes to realize S3. But something that we have is that Z3, to realize Z3, you need qubits. Qubits are not enough because for Z3, the size of the group is 3, so you need 3-dimensional things. But if you look at what they do here, Continuum actually has only qubits. They don't have qubits. So what do? They have to first encode a qubit Hilbert space inside 2 qubits and then do the procedure of constructing the Z3 discrete case. Okay? There are a lot more authors, but I just wrote it like this. Sorry to apologies to all the other authors. Yeah. Yeah, so usually you can write down, so if you concretely write down a set of operators, yeah. So gauging is an operation which is like a projector on some invariant subspace. In some cases, you can realize it as a measurement. So you measure certain operators in the lab. You can think of the measurement as a projector, and sometimes you can set things up in such a way that a particular gauging, which is also a projector onto a subspace of operators, is the same as a measurement you want to do in the lab. Of course, the gauging is not a probabilistic process, while measurement is, but you can compose measurement with some post-selection to make it, if you want. So if you think of gauging as going to the +1 eigenspace of some operators, measurement is you are not guaranteed which eigenspace you fall on, but once you get the outcome, you can act with some unitaries to go to the +1 eigenspace. So this is how what I mean by gauging. Project on the gauging, you also get twisted. That's right. Yeah, so the particular measurements that I'm talking about are ones where you don't have any twisted sectors. The twisted sectors are empty, so you don't get anything new. Yeah. So in that case, you don't have to worry about twisted sectors, but I agree, in general, you will have twisted sectors. Yes.
Can you maybe explain the procedure in the case where you take the trivial theory?
Yeah.
And you gauge it by this finite group, let's say.
Yeah.
And you're supposed to get like a.
That's right. Yeah.
So how to doesn't fit into what you just said.
Yeah, so I will not be doing that gauging. I will go through gaugings explicitly now. I will not discuss that case. That case is a bit subtle because it's a trivial theory with G symmetry acting trivially. I will not consider that. I will consider only faithfully acting symmetries. But that is also a very interesting example to study. I agree. Yeah.
This whole topological symmetry business.
Yeah.
Is acting faithfully or things like that. They're not immediately defined.
I agree that when you want to gauge, acting faithfully is not required. I agree with you. I will only focus on cases where these symmetries act faithfully, just for convenience. It doesn't mean that, in fact, in order to construct any diagram theory from the trivial theory, you need to gauge a symmetry which is maximally unfaithful because it's just acting trivially. I agree with you, yeah. But I will not consider that case here, yeah. Yeah.
So you have some system which is equivalent to a Z2 theory, and then you are trying to make it into an S3 theory.
It's a Z3 gauge theory.
Z3 is a Z3
Yeah.
theory. And okay, so somehow you realize the Z3 theory.
Yeah.
And you're saying you can make some measurements where it behaves like an S3 theory?
That's the point, yeah. Yeah,
That's
you do some certain measurements, which is like implementing a gauging procedure. And then effectively at the end of the day, you get an S3 gauge theory. That's the picture. But the thing that I wanted to highlight in this is that for realizing Z3 itself, actually naturally what you need on the lattice are qubits. But nevertheless, they do it because you can still encode a qubit worth of data into some qubits. So you can still do it. I just want to mention that it requires qubits. Yeah.
This case, so the idea is that you start with this theory of qubits,
Yeah.
and you give it some specific kinds of interactions that are consistent with the Z3 symmetry.
Right.
And then you project onto a Z3 invariant space. Is that the point? And that's like realizing the gauged version of the theory.
Right.
That's the statement.
Yeah, yeah.
And here it was important that the gauge group was finite, like really the gauge group was finite.
Mhm.
Otherwise, it's not something that would make sense, right? You wouldn't usually say that you consider the full non-gauge invariant space and then
Right.
project on. I mean, you could, but that would be you would certainly not want to do that in an experimental setup, right? Because
That's
it
right.
would be infinitely larger.
That's true.
So it's
yes.
important here that it's only finite.
Indeed, yeah. I will look at finite groups, and in fact, because I'm eventually going to this non-invertible symmetries, which is only, as of now, only well understood for the discrete case. And the gauging also is only now being understood only in the discrete case for now. So that's why I'm starting with the invertible case itself, which is the discrete finite groups. Then I will go on to a non-invertible version of a discrete symmetry, not a continuous symmetry. Yeah.
Which I'm missing a little bit, which is that you're saying that, I'm sorry, you're basically saying that in this case, the content of saying you have a gauge theory is just saying that you project onto some finite dimensional subspace of the full Hilbert space. That's all.
That's right. Yeah.
Okay, so there's nothing else that it did for you. There was a global symmetry in the interactions, I guess. Is that
Right?
correct? In the interactions, there was really a global symmetry.
At the level of the it is true that at the level of the Hilbert space is at the end of the day you get some finite dimensional space of space.
Yes.
Whether what these extended operators are like, it now depends on the gauge group, and depending on what the gauge group is, you can get more or less exotic extended operators, and that has some implications for.
I see.
Because the line operators are now what matters.
Yeah, okay. Maybe what is bothering me is that the ungauged theory also makes sense in this
It
case.
also makes sense. Yeah. I mean, the ungauged theory is like anything is a symmetry in that case. I mean, everything is acting.
It's just a theory of some qubits.
It's a theory of some qubits.
And the ungauged theory also makes sense. But
Yeah.
Okay, fine,
Yeah.
thanks. Yeah, maybe if you go on, I'll get a better.
Yeah,
That's somehow bothering me a little bit. Usually, the ungauged theory should somehow not make sense.
But it depends on what the ungauged starting point is. Like for example, if I think about diagram theory as gauging the trivial TQFT, then the trivial TQFT is well defined, partition function 1 on every manifold, and then I gauge a G symmetry acting on it, and I get a diagram theory. So in that sense, it's So then one can ask, can I get DS3 from DZ2? You know, so this was about getting DS3 from DZ3, which is already known that there is a Z2 group. You can gauge symmetry, you can gauge and get it. The question is, can I get DS3 from DZ2? Which would be nice because DZ2, realizing DZ2 only requires qubits. With DZ2, we already saw what DZ2 is. It's a particular BF theory. And if you had a symmetry which you can gauge to go from DZ2 to DS3, that would be nice. The main points of my talk will be that there is no invertible symmetry you can gauge to go from DZ2 to DS3. But there is a non-invertible symmetry you can gauge to go from DZ2 to DS3. So if you decouple at some point, this is the main point I wanted to make. There is indeed a way to construct S3 discrete gauge theory from Z2 discrete gauge theory, but that necessarily requires gauging one of these non-invertible symmetries. Okay, so let's start with what I mean by gauging. So I will gauge only discrete groups in this case. I'm not gauging any Lie groups. I'm not adding any new dynamics into the theory like what we have when we gauge Lie groups. So I'm looking at some G action on operators. And when I say gauging, I mean I'm constructing a new QFT by looking at the G invariant operators of the original QFT. It is not always consistent to define such a QFT, and that is when you have an anomaly. But I will not go more into anomalies in this case. In this talk, everything will be non-anomalous. So it will be consistent to gauge all the symmetries that I talk about in this case. Let's start with quantum mechanics. So almost trivial example, but just to start things off, you take 2 qubits, 4-dimensional Hilbert space. I construct these 4 states, basis states. I just call them 0, 0, 0, 1, 1, 0, 1, 1. I have a Z2 symmetry acting on it, which is just poly X times X acting on this Ij, which is just shifting I and J plus 1 mod 2. So this is shifting mod 2. This is a symmetry acting on your system. What does gauging mean in this almost trivial setting? It just means you look at the invariant states, you get these 2 states. So you just get a 2-dimensional subspace of the full Hilbert space when you gauge. So this is a nice, okay, the Hamiltonian is 0 in this case. So everything is a symmetry. So I could have started with anything I wanted, but I'm just choosing one of them. Now we can go up in dimension. We look at 1+1d QFT. Now the symmetries are a bit more richer, and things that are a bit more richer things going on when you are gauging things. You have line operators which are implementing a symmetry. So I have these topological line operators whose fusion is the same as the group law. So LG and LH are 2 line operators labeled by the group elements. When I fuse, I just get the group multiplication. The action on a local operator is in this form. The picture we can have in the mind is you have a local operator, you have the LG loop. It's a topological loop, so you can shrink it. When you shrink it, the operator changes to some new operator, and that is this LG acting on the point. Okay, so suppose I have a 2D QFT with I already specified to you what these line operators are, or I already specified to you what the action is. Now I have to write down what the gauged theory is. So as we defined before, the gauge theory has local operators, let me call them O prime, which are the operators which are trivial under the shrinking action. So the LG should act trivially, which makes sense because in the gauge theory, that symmetry is trivial. But yeah. Right.
I think my feeling is that doesn't really make sense. But
yeah,
like you need some homotopical notion to take the quotient properly, like you said for a point. I mean, if you take a trivial theory. But can you just explain, like in this case, what do you mean by projecting onto invariant operators? I mean, your operators themselves.
So
the general QFT will have some, like, you have some BRST complex of.
Right. So for me, faithfulness means that there is some operator which is charged, which is on which a given, if you choose one group element, there is some operator on which it acts non-trivially. But you could still have operators which are completely immune to the action of the symmetry. So there can be some operators on which the whole group doesn't act at all. But faithfulness of the action in the definition that I'm using means every group element acts on something. through some non-trivial representation. So you can still have some the trivial representation sitting there in terms of some operators, which are
On some spaces of operators, some
yeah.
subspace.
So some subspace of operators, it can act trivially. But faithfulness for me means can I detect it using something? And it can be the case that there is some operator which is on which this group acts. So it is a faithful action, but there is a subset of operators on which it's acting trivially. So for me, the gauge theory is only made up of those operators.
I'm not really convinced. So if you could have a copy of like a trivial theory sitting inside your story, but you just said that this naive picture won't work for that, but you don't understand why you can ignore
No, I don't
the
see
group
a
acting
problem with
trivially
that.
on some.
No. I mean, you can have trivial action on some subset of operators. But in the example that I'm going to discuss, all the symmetries will act non-trivially on at least something. So I will go to an example in 2D also, which will be the Ising case, just to describe the Z2 symmetry of Ising. Yeah.
But you will tell us what the definition of Q mod you're working.
Yeah. I will compute the in the Ising case and some examples. Yeah. So we can ask, are these all the operators you have in the? Yeah.
You have two operators.
Yes.
Like on which are in this loop acts non-trivially.
Yeah.
In principle, you could kind of bring them both together in a way
Right.
so that you make an operator on which it acts trivially. Right?
That's right. Yeah.
You can kind of cancel.
Right. So all of them I'm calling O prime. So all of them are these O primes. O prime is the set of all operators which are on which the group is acting trivially. So it could be made up of a composite of operators which themselves are transforming non-trivially. Yeah.
So the set of operators, like you're saying they're all closed under some algebra. Is that what is the?
Yeah, the invariant operators will be right, but you can create operators which are not charged under the symmetry by operators which are charged under the symmetry.
Okay. Yeah. Okay. And you will just project onto just this invariant operator.
Yeah. So I will also. That was the next point that you made about twisted sectors. So I will be adding twisted sectors also. Yeah. Okay. So indeed, these are not all the local operators you have after gauging. You have to also consider twisted sector operators. And why do they show up? The reason is that when you had these line operators in your theory which are implementing the symmetry, but there are some point operators which are not actually gauge invariant as a point operator. They are sitting at the end of this line. So this open line, you can have a situation where the open line is not gauge invariant. The point is also not gauge invariant, but this composite is gauge invariant. So there are some operators which are living at the end of the line. And when you gauge this symmetry, you can think about the cartoon you can have in your mind is this line becoming trivial. The line becomes the trivial operator after gauging. But then this local operator, this point operator that you had, which is stuck with this line, becomes a genuine operator after gauging. So this is why if you want to look at the local operators of the gauged theory, it is not enough to look at the local operators before gauging. You also have to look at these operators which can exist at the end of the lines that you are gauging. So this is precisely the fact that you need to add twisted sectors when you gauge. So let's look at an example. So let's look at a concrete example, which is the Ising case. Ising CFT, 3 primaries, 1, epsilon, and sigma. You have a Z2 symmetry, which I'm just calling eta in this case, which is one of the Verlinde line operators you have in Ising. And it is acting in this particular way. 1 and epsilon are neutral under the symmetry, but sigma goes to minus sigma. So because of this action, eta is not is faithful for me. That is in my definition of faithfulness, eta is faithful. It acts on sigma to give minus sigma, but it acts on 1 and epsilon to give, this should be acts on 1 to give 1, acts on epsilon to give 1. This should be the trivial action, and sigma goes to minus sigma. I gauge the Z2. When I gauge the Z2, I get 1 and epsilon as the invariant operators. Something is clearly wrong. When you gauge the Z2 of Ising, you should get Ising back. And 1 and epsilon is clearly not Ising. And the reason is that you have to keep track of twisted sector operators, which you did not do here. So let us look at twisted sectors. If you study the there is, you can
Yeah,
compute
can I
it.
ask-
Yeah.
sorry. I really don't still understand your definition because you said you wanted to act trivially on some operator.
Yeah.
But I could just stack like a trivial theory on top of some theory.
Right?
And the G acting trivially on the trivial theory.
Yeah.
And then I would have, you take your non-trivial theory on which G acts.
Yeah.
Stack on top of it. I mean, tensor it with a trivial theory.
Yes.
And then your definition still applies.
My
But-
definition still applies, but when you gauge, then you will get this gauge theory multiplied by a digravity theory.
Exactly.
Yeah.
So your definition has to incorporate having non-trivial, I mean, your definition has to work for the case of trivial theory with group acting on it. Trivially.
Yeah, I agree. It will work.
So what
That's
is
no
your
problem.
definition for that case? I don't
Yeah.
understand the definition that you're working.
No, no, no. I think in the trivial, so as I said, gauging is well defined even when the symmetry is acting completely unfaithfully. Definition for the, yeah, so in that case also the same definition works. The only local operator you have is the trivial operator. That of course is part of the gauge theory. But in that case, there are lots and lots of Twisted sector operators. When you gauge the unfaithfully acting symmetry, so suppose you are in 2+1d, you have some surfaces acting on the surface operators acting on the trivial theory. There are lots and lots of boundary lines for the surface. So when you gauge, you get a lot of new operators from the Twisted sector. It doesn't come from the operator content that you started with. It comes from the boundary of the surfaces implementing the symmetry. So
How do you compute that? I mean, this is the theory. So in the case
Yeah.
of G, it's true.
Yeah.
You're kind of reproducing the theory of taking homotopy quotients of a point by a group,
mhm.
right? So,
Yeah.
And for higher groups and so on, I guess we'll talk about that. So
Yeah.
I'm just trying to understand what in this language, what is your working, when you say twisted sectors, that's a word.
Yeah.
What does that mean?
Right. Okay. So yeah. So for example, what I mean, the issue is that these operators are not necessarily topological. So I don't know what is the right categorical notion to use. But suppose these endpoints were topological, the notion I'm saying is that the home space from the line operator to the trivial operator, that is some vector space in a fusion category, let's say, and that is the space of Twisted sector operators. It doesn't have to be topological. In icing, it's not topological. Yeah, so in icing, because it's a rational conformal field theory, you can compute a partition function, which is a twisted partition function, and from that you can extract this data. I don't know what is the right categorical definition to be used to incorporate these operators in the setting. Yeah, that usually only works for topological. Yeah, yeah.
That you need to go beyond.
That's right. Yeah. So here you can compute certain partition functions to extract this data from it. Yeah. So that is what this paper does, for example. Maybe there are also older works extracting these particular operators, but I'm just giving this reference because they explain it in terms of, I will explain an action of the eta on these operators. What is the action of eta on these operators? So when you have a local operator, you had a loop shrinking on the local operator. You can still have this action even for twisted sector. So this is a twisted sector operator attached to a line. This is an eta line. You have an eta surrounding it. You shrink this eta. You get another twisted sector operator of eta, but probably a different one. So the line eta not just acts on local operator, it also acts on these twisted sector operators. This is also something that you have to extract from computing these twisted partition functions. And what you find is the action of eta on the psi, these two psi's is non-trivial, but the action of eta on mu is trivial. This is what you find when you compute the action. So then this mu, even though mu was not a local operator when you started, yeah.
Could I just understand roughly what you mean by computing this partition function? Is that you compute the partition function in the presence of an operator, and you look at some, are you computing some correlation function? What are you?
Yeah, so I'm computing, so the usual partition function, let's say I'm computing it on a torus. And then this twisted sector is given by putting, so if this is time for me, this cycle, then twisted sector Hilbert space is given by putting the eta along time, because then I'm cutting I'm cutting along at a given time, there is a twisted Hilbert space corresponding to a cutting of this eta line. And when I'm saying action of the symmetry on this twisted sector, I mean, I put an eta along the other cycle also. So it's a partition function that you have to compute by putting the eta line on both cycles of the torus. Yeah. If you didn't have the eta, it will be the usual partition function.
Okay. And then from that, you're reading of what here? These signs you're reading off from some.
Yeah, so the signs I'm reading, so I will have some expression for this in terms of some characters with some primary labels to it. And then I'm reading off these signs from the coefficient that shows up on this partition function, expression for the partition
So
function.
you're doing the calculation icing here.
In the icing, yeah, I'm just describing icing. And in this particular case, when you compute this particular partition function, you'll get some signs in the partition function for each character that you see in the partition function.
So this is some conformal block expansion from the conformal
Yeah,
feature.
yeah,
Yeah. Okay. And you're looking at the signs, the numbers which multiply the conformal.
Exactly. Yeah.
Okay.
Yeah.
And
So-
and how do you know that this gives you have exhausted the complete set of things doing this?
Yeah. So I mean, once you start with, so the twisted partition function can be written in terms of the ordinary partition function up to some S matrix action.
Sure.
So once you have the original partition function in terms of the three primaries, the outcome will also depend on that data. So you can basically say that the outcome to that calculation is the full set of operators you have. I mean, each of these operators, there's an infinite family, of course. So I'm just calling this the psi tilde and mu are particular representatives for the twisted sector. You can multiply that with any local operator. That is a new twisted sector operator. So these are infinite families. But like in for the local operators, I looked at only the primaries. Similarly, here I'm looking only the representative of each family, which is the psi tilde and mu. And when I say I have to project out things, I mean projecting out the full infinite family from the theory.
Okay, maybe let me phrase it this way and tell me whether I'm getting it right.
Yeah.
You're saying, okay, I know all the primaries in the icing CFT.
Right.
And the Virasura primaries. Mm-hmm. And then, like I just see all the things that I can do within this conformal field theory.
Yeah.
Okay. And that's how you exhaust all the things.
That's right. Yeah. Yeah.
Yeah. The problem is that like there's no reason that you should be in the conformal field theory, right? You could kind of.
Yeah. So here I'm looking at the continuum. I'm not going to I'm at the conformal point, and I'm giving an example only at the conformal point. In general, yeah, there's no.
Like many maybe operators just go away or become identified.
True.
When you go to the.
Yeah, definitely. Yeah, I agree with you.
So that is okay. So
I just want to give one of the simplest CFTs just to highlight the fact that you have to throw out some things, you have to include some things, which you already, of course, mentioned, but I just want to give an example of that.
Okay.
Because we will do like a 2+1d version of this.
Okay.
Yeah. So when you gauge this eta, psi and psi tilde gets projected out because they are charged under the symmetry. But mu now becomes a genuine operator. And this is why you get icing back when you gauge Z2. 1 and epsilon was already there. Sigma got projected out, but mu joined your set of local operators. So you got back icing because mu has the same scaling dimension as sigma. So these are the order and disorder operators that you have in the icing model. So this is an example of a self-duality under gauging a symmetry because you got the same theory back. Okay, so what happens in 2+1d? So the story will be very, very similar, but now the operators which are implementing the symmetry go one dimension high. In quantum mechanics, it was points. In 1+1d, it was lines. Now it will be surface operators. So you have topological surface operators whose fusion is given by, let's say, some group. I have an action of this surface on lines. I can also have an action on points. But the theory that I'm interested in is digravity theory, which do not have any local operators. So I will be describing the gauging process for lines when surfaces act on lines because there are no local operators in the theory I'm interested in. So when a surface operator acts on a line, the picture you can have is a line comes in and it gets transformed into a new line when it passes through the surface operator. You can have another picture also of this, which is not on a closed manifold. You can have the surface on a torus. You put the line inside the torus, and you can shrink the torus on the line to get a new line. This is also a valid description, but I will use this way of defining the action on lines. What does it mean to gauge the surface operator? If I gauge, again, I have this picture where the surface operator becomes trivial. So before gauging, I had line L1 and L2, which are related to each other by the symmetry. When I gauge the surface, those lines get identified. That means Li and Lj admit a junction now. When you forget about this Sg, you have gauged Sg, you have introduced a junction between Li and Lj. So there is a way to go between Li to Lj and back. So they are the picture is that they are the same line operator. You have identified them in the gauged theory. Are these all the line operators you have? The same question that we asked in 1+1d, and the answer is no. These are not all the line operators. You have to consider twisted sector line operators. When you have topological surfaces, they can have topological lines or even non-topological lines bounding these surfaces. When you gauge the surface becomes trivial, and this non-genuine line operator becomes a genuine line operator after gauging. So this is like adding twisted sector local operators in 1+1d, but now you're adding twisted sector line operators when you're gauging a symmetry. There's a bit more complication about the gauging process where a line operator splits into a sum of lines. This is something that happens in this dimension. Basically, what happens is if you have a surface acting on a line and the line goes to itself under the symmetry action, when you gauge the surface, you introduce a local operator from L to L. So you can think about this. Suppose this L is a topological line operator. You can think about the L as a quantum mechanical system. You have the surface operator acting on the L. This junction is also topological because you can move S along the line because S is topological. So this junction also moves. So this point, the black point, is also a topological operator acting on the quantum mechanics of the line. That is a picture you can have. Now the thing is, when you have multiple surface operators acting trivially on a given line, you have many symmetries on this quantum mechanical line. So the line splits into a sum of lines. Why does it happen? If you have a quantum mechanical system with a symmetry, you can split the Hilbert space into just the representations of that symmetry. That's a direct sum. And it's the same thing that happens in this case. If you have a bunch of surfaces which acts trivially on a line, after gauging, the line splits into a sum of lines. And the splitting is given by the representations of the CL. And the idea you can have in your mind is that this L is just a quantum mechanical system. The point which came from this junction here is a symmetry acting on L. And whatever algebra the point has, the L splits into a sum of universes corresponding to representations of the symmetry. That's the idea. So this is something that happens in this dimension. So these are some of the ingredients that goes into gauging symmetry implemented by surfaces in 2+1d. Now, let us go back to the theory that we started with, which was the Z2 Dagger-Witten theory, or on the lattice, the toric code. It had these line operators. This was the data of the braiding data of the lines. All of these lines are order 2. Everything is an order 2 operator in this case. What is an invertible symmetry in this case? What is an invertible symmetry of this model? An invertible symmetry is some action on the lines so that all of this data is preserved. So this S matrix spin our physical gauge invariant information. If you try to act with some symmetry, it better preserve this gauge invariant information. And there is only one thing you can do. You can permute E and M with each other. E and M are both bosons. If you flip them, clearly this is preserved. And you can check that if you just flip E and M, this matrix is also preserved. And you can show that everything in this theory is determined by this data. So as long as you preserve this, it is a symmetry of the theory. So you can flip E and M. And the gauge theory, this is just flipping the two gauge fields. So it's the EM duality of the Z2 gauge theory. So the EM duality of the Z2 gauge theory is a Z2 symmetry, which permutes E and M. And this is an invertible symmetry. Now, you can ask, this is the only invertible symmetry, in fact, which is acting faithfully, in the sense that this is the only symmetry which which permutes lines in this theory. There is only the Z2 symmetry. You can try to gauge it, and the outcome will not be the S3 gauge theory. Okay, I can explain why this is not the case, but let me go to the non-invertible case because, well, maybe I can spend some time. It's 1.5 hours, maybe. Okay, great. Okay, so you can try to gauge this symmetry, which will be a nice exercise to look at the rules that we wrote on earlier, and you can find that the answer is not S3 gauge theory. How do we know that? Let us gauge. So 1 goes to 1 under the EM duality surface. E goes to M under the EM duality surface. So when you gauge, what is the rule? 1 goes to 1 under both the trivial surface and the EM duality surface. So 1 splits into 2 lines. This is one part of the gauging process. So 1 splits into 1 and 1, 2. Maybe not the best notation, but 1 splits into 2 lines. Psi, the fermion, is also a fixed point under the Z2 action. It also splits into 2 lines. E and M are identified under the Z2 symmetry. So they are, I'm just calling it something like an equivalence class because they are identified under the Z2 symmetry. So after gauging, they become the same operator. This is the set of line operators. I already have 1, 2, 3, 4, 5 line operators in the gauged theory. But these are actually not all the line operators. What did we forget? We forgot twisted sectors. So we look at twisted sector of the EM duality surface. Now, I will skip the part of how to really construct these sigma plus and sigma minus. The main point is that you can write down this operator explicitly using a gauging procedure, which is a different type of gauging. And from there, it will be explicit that there will be 2 boundary conditions to this surface operator, which I'm just calling sigma plus and sigma minus. These are topological boundary conditions. Everything is, it's a completely topological theory. Every twisted sector is also topological in this case. Sigma plus and sigma minus are 2 topological line operators, which are not genuine line operators. They exist only at the boundary of a surface operator. Okay. When I gauge this, they also become genuine operators. But in this case, the action of SEM on sigma plus and sigma minus also happens to be trivial. So you have to split sigmas also. So the rule that a line should be split when the action is trivial applies to twisted sector operators also. Before gauging, you had 2 line operators, twisted sector operators on which SEM acts trivially. After gauging, they become 4 operators. So this is where I'm skipping some details, but the point is that you get 4 lines from twisted sector. So you already got 5 lines from untwisted sector. You got 4 lines from twisted sector. You got 9 line operators. Clearly not the S3 discrete gauge theory that we want because it had only 8 line operators. When I wrote down all the lines in the beginning, it was only 8. You got 9. So this is not, from just counting the line operators, we know this is not S3 discrete gauge theory. In fact, it is known what this, after gauging, you basically get a cousin of the icing. It's something called icing times icing bar. That is what you get in 3D. This is the outcome. But the main point that I just want to make is that it is not the S3 gauge theory because you have too many lines. Questions on this? This may be a bit quick, but yeah. So you have only one faithfully acting symmetry in this model. You tried to gauge it. You did not get what you wanted. Okay, so let me write down a non-invertible symmetry. Now this is, you are doing some violent operation now. Yeah.
That's why, I mean, you can generally make a statement that in other cases also where non-invertible symmetry will not lead to this D of S.
Yeah. So indeed, I can also, so this was, Z2 was the only faithfully acting symmetry, but I can indeed consider symmetries which act trivially also and try to gauge them, which I can choose any group, basically. I can choose any group which acts trivially on the 4 line operators and gauge them. But in that case also, there's an argument showing that it did not be the S3 discrete gauge theory, which I did not go into. But the only faithfully acting symmetry is Z2. Gauging that will not give you S3 discrete gauge theory. Any unfaithfully acting symmetry also will not give you S3 discrete gauge theory, but I did not explain why that is the case. Yeah. I mean, there is also a counting you can do in that case. Basically, you will see that because S3 discrete gauge theory has only 8 line operators, even if you are gauging an unfaithfully acting symmetry, that symmetry cannot be too big. It will be bounded above. So you'll have Z2, Z2 times Z2, things like that. And you can basically work out each case and see that it will not give you the right thing. Okay, so now I'm going to use a new symmetry, which is also there in the toric code, in the Z2 Dirac-Witten theory, which acts in a non-invertible way, clearly because there's a 0 coming out there. This is not a usual permutation that you have. 1 and E, the line operators 1 and E goes to the sum of lines, 1 plus E. But when it acts on M and psi, you just get 0 as an outcome. So this is a weird action where you are just killing some line operators in your theory. Okay, I can write down this, but do I know that there is an operator which implements this symmetry? Is it really a symmetry of the theory? So there are various ways to check that this is in fact a theory, it is in fact a symmetry of the theory. One thing is it consistent to have this as a surface operator in your theory? That is one question we can ask. So suppose I have a surface operator S which implements this symmetry. This S is acting on L to give L prime for some line operators. And on both sides, I have the Z2 discrete gauge theory. So this is the picture I have. Now, there is a procedure which is sometimes called the folding trick, where you start with this and you fold from this picture to what you have here, where you convert an interface into a boundary condition. So you have an interface between two theories, you fold it, you get a boundary condition. Now, if L and L prime are related by the symmetry, after folding, L prime comma L, this is a line operator of this theory, it should be able to end on this boundary condition. So this boundary condition should be defined by the endability of L prime comma L. So if S was acting in this way, the folded theory must have a boundary condition on which these line operators can end. 1, 1, 1, E, E, 1, E, E. Why is this list? Because this is how S acts. S acts on 1 to give 1 plus E. So there's a junction between 1 here and E here. There's a junction between 1 here and 1 here. There's a junction between E here and E here, etc. So when you fold, this L prime comma L takes 4 values, 1, 1, E, E, 1, E, E. And there should be a boundary condition which is defined by these line operators. And indeed, there is a boundary condition which is defined by this endability, which is worked out in this paper. So this is one way you can check that this surface operator is consistent, because when I fold it, I got a consistent boundary condition. This is one way to check whether your interface is a consistent one or not. There are at least 2 other ways to construct this surface operator explicitly and to find the action of that surface operator on the line, and you will get this action. So there is a procedure which is sometimes called higher gauging, which is a way to construct S, and you can study the action of S on the line operators, and you can basically say that, I mean, this one more method, but there's also other methods. So there are multiple arguments which shows that this is indeed a valid surface operator in the theory, even though its action is very weird. It is putting some lines to 0. But in this picture, this is not a weird thing to say, because what does 0 mean in this picture? 0 means that if I have a surface operator and if I put M here, there is no other line I can put here so that this junction exists. That is what the 0 means. M can come in from here, but M can never become a genuine line operator. This is what the 0 means. So at the level of configuration of defects, this is not a drastic thing to say. But at the level of a symmetry action, it looks drastic because you are killing some operators when you define the symmetry. This is not the only non-invertible symmetry of this model. There are a few more, but this will do the job for us. So I will only discuss this one. Every single non-invertible symmetry, when you fold, you will get a boundary condition. Yeah.
All the non-invertible symmetries are right.
In this case, also in topological theories, they also arise by unfolding boundary conditions. Yeah. But you can have boundary conditions which you cannot unfold, because to unfold, this theory must be this product form. So sometimes you can have boundary where the bulk is not this product form, so then you cannot unfold it. So there are more boundaries than interfaces. These interfaces. That's true. Yeah. Yeah, you can make it an interface between two different theories, indeed, but you cannot map every boundary to a surface operator in a TQFT, because then by definition both sides should be the same TQFT. Yeah. Okay, so there are more methods to verify that this is a consistent surface operator, but let me just go ahead with this action. Okay, I want to gauge this symmetry. So I do the same procedure as we had before. I look at the action of this S on the line operators. 1 goes to 1 under S, but also the trivial surface acts trivially on 1. So the line 1 should split into 2, as we discussed by the splitting rules when you gauge. E goes to E under the surface S. Why do I say E goes to E? Because even though the action is like this, there is an input E here and there is an outcome with E. That is why what I mean by there's a junction between E and E on the surface. So the outcome is 1 plus E, but you have to take one by one. What are the junctions, possible junctions you can have? That is why I'm saying E goes to E is a consistent junction. E goes to 1 is also a consistent junction. I will come to that. So 1 goes to E is also a consistent junction, indeed, yeah. So first we look at 1 goes to 1 and E goes to E. 1 and S acts trivially on it. These two split into 2 each. So you get 4 line operators. So you get these 4 line operators. But as was mentioned, 1 goes to E and E goes to 1 are also consistent junctions. So it's not enough to split it. There are some identifications you have to do. Without loss of generality, I'll just identify E2 and M2. Sorry, I may have made a mistake here. Let me think. Yeah, sorry. So here it should be, yeah, sorry. So here what I mean is that 1 goes to E and E goes to 1 is a constant junction. So I have to identify one line operator here with one line operator here. So I'm just identifying 1, 2 with E2. Sorry, this was not the right thing to write. So yeah, what I meant is that 1 splits into 2, E splits into 2, but because 1 goes to E and E goes to 1, you have to identify one of the 1, 2 and E2, let's say, with each other. You can choose any of these line operators. You just identify 2 of them because there's a channel between 1 and E. E and M is not a consistent junction here. So sorry, this was completely not the right thing to write here. This was the case for the EM duality action. But yeah, here it should be E2, 1, 2. Okay. So I get these line operators. I get 1 subscript 1, E subscript 1, 1, 2, E2. These are the lines I got so far by gauging the surface S. Okay. 1 split into 2, E split into 2, total 4, but you identified 2 of them, so you get 3 line operators total. Okay. What are the fusion rules of these line operators? E1, when you square it, you just get the trivial line. Why do we know this? This is because E itself was order 2, and E1 came from E, so its order is also 2. How do we see that? Just think about some interface between the theory before gauging and the theory after gauging. And this I is like the gauging interface that is implementing this gauging between 2 theories. E1 came from E. E1 came from E. You take 2 copies of E1. These are 2 lines which are crossing through the interface. On the other side, it becomes E because E1 is not a line operator in the original theory, it is E. You fuse parallelly like this. On the left-hand side, you will get E1 times E1. On the right-hand side, you will get 1 because E square is 1. So whatever E1 times E1 is, its image should be 1 in the ungauged theory. What is that line? It's 1 subscript 1. That is why you can deduce this fusion rule from this configuration. Questions? Yeah. That's right, yeah.
Is it basically just that on one side, the line the Wilson groups are computing traces of polynomials in a particular representation. In this case, the group is discrete, so it's different. And then when you cross that surface defect, you're applying a map of representations, changing the representation.
Yes. Yeah.
Mathematically, you're looking at the category rep G and looking at some two objects in rep G and saying there's some map.
At the level of rep G, it will be just the induction and restriction maps. That is what it would be. Yeah. But there is, of course, more lines than rep G. So it's some generalization of that. But yeah, at the level of rep G, it is induction and restriction. Yeah. So this is how we know that E1 squares to 1. Okay. Now we want to get this fusion. We do exactly the same thing. Okay. We do exactly the same thing. You choose 1, 2, E2, 1, 2, E2 here, which is the line operator after gauging. Before gauging, it came from 1 and E, because it came from identifying 1 and E. So 1, 2, E2 is a line operator which comes from 1 and E. Again, another copy of this. You fuse, same as before. On the left-hand side, you got this product. On the right-hand side, you got 2 copies of 1 plus E, because both 1 and E are ordered 2. So you just multiply them, sum, you get 2 copies of 1 plus E. So whatever this is, when you pass it through the interface, it should be 2 copies of 1 plus E. Then you try to write down what that is. So 1, 1, you pass it through the interface, you get 1. E1, you pass it through the interface, you get 1. Sorry, E. 1, 2, E2, you pass it through the interface, you get 1 plus E. So this is 2 times 1 plus E that you get if you pass this through the interface. Now this should be nice, because this fusion rule is precisely how the S3 representations multiply with each other. 1, 1 is a trivial representation of S3, let's say. E1 is the sign representation of S3. This is the 2-dimensional representation of S3. This is precisely the tensor product of representations for S3, which would be nice indication for what we want to do. So this set of lines that you have is actually rep S3. This S3 Wilson lines that you have in the S3 discrete gauge theory is what you have got by this procedure. Now, that is not the end of the story, in fact, because we know that the S3 discrete gauge theory has a lot more lines than just the Wilson lines. What happened to them? Story is the same. We forgot about the twisted sector line operators. This is where I will have to skip some parts, because now it gets a bit more complicated as to finding these twisted sectors. But what I want to ask you is the gauging actually consistent? Because when we define the gauging process, we said if 2 lines are mapped to each other under the gauging, you identify them. But there are some lines which are killed by the surface. So what does it mean to gauge? Like, what happens to M when you gauge S? Because M is becoming 0. So our procedure, there's some issue with our procedure. Now, the resolution to this is that this is not the full action of the surface operator on the lines. This is exactly what happened in Ising. In the Ising model, there is a non-invertible symmetry. If you're familiar with the sigma primary corresponds to a non-invertible symmetry in Ising. And that, in that case also, the action is by 0 on the Hilbert space. But really what that 0 indicates is not that you have a 0, is that a local operator is being mapped to a twisted sector operator. That is what happened, what is the resolution Ising. And that is exactly what happens here. When I say M and psi are 0, the reason why you got 0 is because you are only looking at the space of genuine line operators. If you consider the action on genuine plus twisted sector operators, you will not find zeros. In fact, the full action of the surface will not have zeros at all. The full action is this. On 1 and E, you get 1 plus E. everything is okay. On M and psi, initially we thought it is 0, and it is, you will get it as 0 when you compute it as an action on the genuine line operators. But if you include the twisted sector of S, similar to the EM duality, here also you will find that there are two twisted sectors. I'll just call them X and Y. It is, at this point, is some abstract label, but if you actually look at the construction of this S, again using this procedure called higher gauging, it will become clear that X and Y are the two boundary conditions you can have for the surface. But here I'm just calling them some abstract labels. There are two boundary lines you can have for the surface S. What is actually happening is that M and psi are getting mapped to X, one of them. It doesn't have to be X. So this is the actual action. There is also an action of S on X and Y also, similar to what we had in the icing case. So here you can see that this is actually what the action is. You have to look at the non-invertible symmetries are symmetries which map local operators to twisted sector operators, or genuine line operators to twisted sector line operators. So when you study the action of non-invertible symmetries, it is crucial to look at the action on not just genuine operators, but together, along with the genuine operators, you have to also study the twisted sector operators. Otherwise, you will miss out on some details of the action. This is true in 1+1d and also true in 2+1d. Now, you don't have any zeros anymore. You can apply the procedure of gauging to this action now. Look at what is being identified to what, split lines accordingly. For example, Y goes to Y 2 times. What does this 2 mean, for example? What do I mean by Y goes to 2Y? I mean, when Y comes in, Y can come out, but the point is not one-dimensional anymore. There are two-dimensional space of operators that you can have on the point. That is what this 2 means. But details aside, you can basically repeat the procedure that I mentioned earlier, that when two lines are identified under the symmetry action, when you gauge, you identify them. If a line is invariant under the symmetry action, you split them under gauging. If you use that, you will get the following. 1 goes to 1, 1 plus 1, 2, as we had before. E goes to E1 plus E2. M goes to M, psi goes to psi. Why is that? It doesn't split, because M and psi are mapped to something else under the symmetry action. So M and psi doesn't split. X splits into 2, Y splits into 3. Why is it 3? 2 of them comes from the fact that the surface S acts on Y, gives 2Y. But there is also the trivial surface, which is acting trivially on Y. So when you are gauging, you have to also keep track of the trivial surface. That's why you get 3 Ys. Now you have to identify things like we did before. For example, initially we identified 1, 2, and E2 before doing this general case. You have to look at cases where you have to identify X. For example, in the previous slide, you had M goes to X. M did not split under gauging. X did split into X1 and X2, but they are not independent because M goes to X under S. So you have to identify one of the X, X1 or X2 with M. Similarly, you have to work out all the identifications. Yeah.
Particular action that gives ES3, or you can take any other. I mean, for instance, if you don't have this 2 over here, specifically the factor of 2.
Yeah.
You still get the DS3.
Yeah. So there are parts of this action which are completely fixed by the surface operator and parts which are not. If you change, gauging is not, that is an important point, because gauging is not a unique operation. You have to choose some extra data. In 1+1d, you will call it a discrete torsion that you have to fix to gauge. In this case also, there is some freedom. In this particular case, when you gauge using the discrete torsion, what happens is that it is still an S3 discrete gauge theory, but an S3 discrete gauge theory with a digraviton twist. So it's a different theory, but the same gauge group. The action is different. So, but more generally, you can have cases where you change this action consistently, because action on the genuine operators is completely fixed, but the action on the twisted sector operators is not completely fixed. There is some redundant data. Depending on what you choose, it could be the case that you get different theories indeed. In this case, the change happens to be a bit mild. The gauge group is the same, but the theory can be different. Yeah. So yeah, so in the category, I would say that you have to choose an algebra. Okay, okay. Yeah.
What is it?
Yeah.
If I take a theory,
Yes.
not even non-topological theory, whatever, some theory,
Yeah.
and I have some subset of topological operators,
Yeah.
which is closed under OPE,
Yeah.
then I should be able to gauge, right?
You should be able to gauge. It's just that when you define gauging, you define it as looking at the invariant operators. So to say what is an invariant operator, you have to define the action of the symmetry on all the operators. Even though the action of the operator on genuine operators are fixed by the defect that is acting, the action of the operator on twisted sector, there can be some redundancy in that. For example, in the 1+1d case, when a symmetry acts on twisted sector Hilbert spaces, you have some freedom of adding a 2 cocycle in that action. And depending on what you choose that 2 cocycle to be, after gauging, you can get different theories. So it is still consistent, but gauging is not a unique process. It doesn't give you a unique
2 cocycle? 2 cocycle where?
Yeah, so 2 cocycle shows up when you, yeah. So
Talking about Digraph-Witten theory or?
yeah, no. So in 1+1d, I mean for a general symmetry, you are trying to gauge.
Yeah.
You can add some data. You can add some H2 GU1 data, some 2 cocycle data, when the lines act on local operators, twisted sector operators.
And H2 of what?
H2 of the discrete group BG, let's say, in U1.
But I don't have a group, right? I have some set of topological operators, possibly not.
That's right. Yeah. So in
also.
that case, it's a choice of trivialization of the F symbols for your fusion category.
Okay.
Which may not be unique. And depending on the choice of trivialization, you'll get different gauged theories.
Now, the gauge theories, are they genuinely different, or are they just, do they look different? I mean, they could be equivalent, they could be dual.
It can happen that the gauge theory actually happens to be the same, but in general, they are genuinely different because the operator content and correlation functions of the gauged theory will change depending on your choice of this extra freedom.
I see.
Yeah, but this extra freedom is also always a discrete choice. So you will get a finite number of gauged theories, but they can be different.
I mean, let's say content of the operator.
Yeah, they can be different in the content of the operators. So in general, they'll be different. But these things are all subtle in the sense that there are cases where you choose 2 different discrete torsion, you gauge, you get the same theory back. That can also happen. In general, you will get different theories. Yeah.
Actually, I still don't fully understand the physical content. So you're saying something about fusion categories, but fusion categories are a very special case when you're looking at topological operators, I guess, in some particular dimensions. In general, the topological operators will organize into something more complicated.
That's right. Yeah.
So it's what is this? What is the meaning of this F symbol physically?
Yeah. So the F symbol description only applies to 1+1d.
Yes.
Where the symmetry is in line operators.
Then,
in 2+1d, when I have surfaces, it will not be the F symbols. It will be some other data defined by the associator for the surface operators. I don't think.
So it's a choice of an associator? Is that what?
It's a choice of the trivialization of the associator for the surfaces.
But if you do all this properly homotopically, then you'll have a coherent system of trivializations.
Right.
So, and that space is usually contractible in most situations. I don't know what. So what is the ambiguity exactly? Like, what is the ambiguity captured by physically?
Yeah, for surfaces, I don't know a full answer to that question in 2+1d. I know that abstractly, I know that it is the same as the data corresponding to an algebra in a 2 category. But it has not been unfolded, at least in my mind, I haven't unfolded a definition enough to give you a physical intuition as to what that constraint is. Yeah. At the end of the day, it's about, when you think about gauging as putting a network of surface operators, it should not depend on the triangulation or the whatever simplicities you use. Gauging should not depend on that.
But then you're supposed to, you can always take a kind of, increasing union of all possible triangulations. And take a co-limit in some sense. We can discuss that later, maybe.
Yeah, okay. Okay, so yeah, so the final thing I will say is that, okay, after you identify all the line operators that you got, 1, 1, E1 that we had initially, 1, 2, E2 that we identified initially, there are also a few more identifications. M you identified with X1, psi you identified with X2, and Y1, Y2, Y3 turns out is not identified with anything else because nothing is mapped to Y under the symmetry action. You get 8 line operators. We already saw that 1, 1, E1 and this line forms rep S3 under fusion. You get the total number of lines is 8. These 2 data points are enough to conclude that the outcome is the S3 discrete gauge theory. So this is the main point, that you gauge, you have this particular symmetry that you gauge, which is a symmetry that mixes things around a bit more, right? It mixes genuine line operators with non-genuine line operators. But once you gauge it, you get 8 line operators, which are the line operators of the S3 discrete gauge theory. Okay. So let me just summarize by just highlighting some of the things that I mentioned, that you can have, so this was a very simple case of a TQFT, where you have 2 TQFTs which are not related by any ordinary gauging, but there was a non-invertible symmetry. When if you gauge, you can relate them. This is much more general. You can have situations where these operators show up in a QFT and you gauge and you get new relations between QFTs which you did not have just by looking at ordinary symmetries. And the point that I did not discuss in this case are cases where you cannot gauge, which is also very interesting because then you have anomalies, and they are also important for studying RG flows. So this was a case completely about things when you can gauge, but even when you cannot gauge, they are very, very interesting. Now, what is a future direction? Something that we are looking at right now is to actually, we only did this in the continuum. We want to realize this gauging on the lattice to connect back to the papers that I was mentioning in the beginning, where they actually did stuff on the lattice.
Can I ask a question? So once you're finished with it, once you have the 8 line operators,
yeah,
is there something in the final theory which tells you that there's some other non-invertible symmetry which led to this theory?
Yeah, great. So there is a dual symmetry. Like in the 1+1d case, when you orbifold, you get a quantum symmetry, right? Dual symmetry. In this case, you started with this S acting on the Z2 gauge theory, you gauged it, you got S3 gauge theory, which had these line operators. This has a dual symmetry, even though it's not obvious, in the sense that these lines are all topological. So these lines are themselves symmetries of the S3 discrete gauge theory. In particular, there is a gauging that you can do to go back to Z2 gauge theory. That gauging is actually gauging this 1, 2, E2. There is a symmetry. 1, 2, E2 is not an invertible symmetry because 1, 2, E2 is not an invertible line operator. Its fusion is the S3, two-dimensional representation of S3 fusion. You can gauge this 1, 2, E2, which is the inverse of gauging that we did to come back to S3. So S3 knows that you can create it from Z2 in this sense. But you can create S3 from many, many, many ways. Many theories you can start with and get S3. And all of that depends on what can you gauge in S3 to go back to those theories. So all of these operations are invertible. Yeah. In general, it is expected that they should be invertible in this sense. Yeah. So this would be called a non-abelian anion condensation in the condensed matter literature. Yeah.
So the statement is that, so the non-abelian anion, so the statement is that you start with this theory. If I can condense a non-abelian anion, go into some theory.
Yeah.
Then there is a non-invertible symmetry in the theory that I can gauge and come back here.
Right.
Is that the statement?
Whether the thing that I have to gauge to come back is invertible or non-invertible depends on what you gauged to go to that theory.
Okay.
Sometimes the inverse can be an invertible symmetry gauging.
Right. But there will be something there.
There will be something.
Yeah. So what tells me that when will that thing that I have to gauge be non-invertible? What is the property of this non-abelian
Yeah.
Any on that?
Yeah. So usually when people say about gauging 1, 2, E2, when you fuse 1, 2, E2 with itself, it's like S3 fusion. So you will get 1, 1, E1 and 1, 2, E2 back when you fuse.
Okay.
There is one gauging where you gauge this set of lines, which are closed under fusion. If you do that, you will get the trivial theory.
Yes, you're just taking all of S3.
You're taking all of S3. So the inverse is gauging the S3. Gauge zero from symmetry, come back to diagram. The gauging you have to do to get toric code, this Z2 theory, is gauge this, but do not gauge E1. There is still a notion of gauging this non-abelian 1, 2, E2 without gauging E1. Even though E1 is an outcome of a fusion of this composite line with itself. So the thing is, the set of lines you are gauging do not have to be closed under fusion. Gauging is a more general operation. And whenever you gauge lines which are not closed under fusion, the inverse gauging will be non-invertible. I mean, inverse symmetry that you have to gauge will be a non-invertible symmetry. Whenever you gauge line operators which are closed under fusion, the inverse zero form symmetry gauging is an invertible symmetry. Yeah. That is the general criterion.
Okay. So I'll just ask, so is this like, can I always think of some non-invertible symmetry in a theory this way, that I kind of, there is some.
If they are non-anomalous, it
if
could
they're
be
not
that you cannot
anomalous.
get it from any other theory if they are anomalous.
Right.
Yeah.
Uh-huh.
Like there are other surface operators in the Z2 gauge theory, which I did not talk about. Many of them are anomalous. You cannot gauge it. So those I don't see how to get it from another theory. Yeah. I mean, the thing is, gauging will make it, you can get it from another theory in a way, but in the sense that you can start with a theory, gauge something else, and get a new theory. And this anomalous theory will remain in that new theory as some other symmetry, still with that anomaly somehow there. But in this sense, I don't see you will get it.
No, so what I'm trying to get at is this some way of at least classifying some class of non-invertible symmetries, that you kind of do this thing where you kind of gauge some things, but not the full, not closed under fusion. So that is a way of classifying what non-invertible symmetry that I can have, at least a subclass of them, or.
Yeah, so there is a classification which is too general in the sense that it can happen that the inverse symmetry is unfaithful. Like if you gauge these three, you get the trivial theory where the S3 is acting on it. In this sense, you can create any group acting on the trivial theory by starting with the diagram theory, gauging a rep G, going back to the trivial theory, right? So there the classification, even for the invertible case, is any finite group. Similarly, if you do this for non-invertible things, it will become a huge list of things, which is a much more bigger generalization of a finite group. Maybe you want to put the criterion there to say, oh, the dual symmetry that you need to gauge to come back should act faithfully. If you put that extra condition, this huge set becomes very small. Like in the Z2 case, it becomes just a Z2 symmetry, EM duality. Similarly, in a general case, you can completely classify those faithfully acting symmetries. If you forget faithfulness, you can act with many, many things.
Yeah. Okay.
Yeah. So
it's kind of, yeah.
Right.
You can always add any number of trivial theories.
Yeah, exactly. So, but once you assume faithfulness, yeah, there is a concrete classification. Thanks.
I had another more trivial question.
Sure.
I asked about that lattice
Mhm.
model and connection to the digraph.
Yeah.
With